Hello and welcome to 4.3 Derivatives and the Shapes of Curves. In this section we'll be looking at how derivatives can help us graph certain functions. We start off with the mean value theorem, which tells us that if f is a differentiable function on the interval from a to b, then there exists a number c between a and b such that if we do the average, we end up with the derivative at point C. In other words, if we take an average between a f of a and b f of b, and we do an average slope, somewhere along the line the slope will equal that average slope. There will be a point C at which the average slope is equal to the instantaneous slope. Okay, there'll be at least one point that is like that. Here we see we have 2 points where the instantaneous slope is the same as the average slope. Okay, so velocity, if you're looking at an example with velocity, for example, if a car traveled 180 kilometers in 2 hours, the speedometer must have read 90 kilometers per hour at least once during that time. At least once. Okay, and that's an application of the mean value theorem. Increasing and decreasing functions. If the derivative is greater than 0 on an interval, then f is increasing on an interval. Okay, so the original function is increasing on an interval. If the derivative is less than 0, so it's negative on an interval, then the function is decreasing on that interval. Okay, and that leads us to the first derivative test. Okay, so in the first derivative test, if the derivative changes from positive to negative at a point, then we say that the function has a local maximum at that point. If the derivative changes from negative to positive, then we have a local minimum at that point. If the derivative does not change signs at C, then there is no maximum or minimum at the point. Okay, let's take a look at examples 2 and 3. Find where the function is increasing and where it is decreasing. And a follow-up, find the local minimum and maximum values in this example. Okay, so let's first take the derivative of our function. Just take the power rule for each term. So here we would have 12x cubed minus 12x squared minus 24x. Okay, and now what we're going to do is we'll set this, set it equal to 0. We want to find any critical points. To help us, we could factor, right? In order to solve this, we could factor out of 12x. That means we're left with x squared minus x minus 2. Factor the inside trinomial further. So that would be negative 2 plus 1, so x minus 2, x plus 1. Okay, now setting each of these factors equal to 0, we get x equals 0 for the 12x. X minus 2 equals 0, so x equals 2. And x plus 1 equals 0, so x equals negative 1. Okay, so now let's do our first derivative test. So draw a number line. Okay, we have 0 and negative 1. And 2. Now what we want to do is, we know the derivative is equal to 0 at these 3 points. We want to find out what's happening around these points. Okay, so we'll do what we call test points. We'll pick a number to the left of negative 1. Like let's say negative 2. We'll pick a number between negative 1 and 0. Let's say negative 1/2. Pick a number between 0 and 2, 1. And then pick a number to the right of 2, 3. Okay, and so we'll plug in these values into the slope formula. Plug it into the factored version. It makes it a whole lot easier. And that'll tell us whether the function is increasing or decreasing in those intervals. So let's first plug in negative 2. So we have 12 times negative 2, negative 2 minus 2, negative 2 plus 1. So what does that give us? That's negative 24 times negative 4 times negative 1. So that's 96, negative 96. Okay, so that means in this range to the left of negative 1, we have a negative. It's decreasing. Okay, plug in negative 1/2. So 12 times negative 1/2. Negative 1/2 minus 2. Negative 1/2 plus 1. Okay, so that's negative 6. Negative 1/2 minus 2, that's negative 5/2. Negative 1/2 plus 1, plus 1/2. So we have negative times negative, that's a positive. And positive times 1/2, that's a positive. Okay, so that gives us increasing between negative 1 and 0. Let's test 1 out. So 12 times 1, 1 minus 2, 1 plus 1. So that gives us 12, negative 1, 2. That's 24 times negative 1, negative 24. So it's a negative. Next, let's plug in 3. So 12 times 3, 3 minus 2, 3 plus 1. So that's 36. 3 minus 2 is 1. 3 plus 1 is 4. That's 144, so that's positive. Okay, so this tells us that the function is decreasing from negative infinity to negative 1, increasing from negative 1 to 0, decreasing on 0 to 2, and then increasing on 2 to infinity. Now, in terms of maximum or minimum, if it's decreasing followed by increasing, we have a minimum. Okay, we'll investigate that a little further. If we go from increasing to now decreasing, that's a maximum, local max. If we go from a decreasing to an increasing, that gives us another local minimum. Okay, so in order to declare the maximums and the minimums, we need to figure out the y values as well. Okay, these are going to be the x values where the max and mins will occur. So now we have to go in and figure out the y values. Okay, so we have negative 1, 0, and 2. Okay, and you'll use this, use the original function. Okay, use f of x. Just plug these in, and you'll get the corresponding y values. Okay, so if we plug in negative 1, we'll get 0. If we plug 0 in, we'll get 5. And if we plug in 2, we'll get negative 27. Okay, so we say local minimum at negative 1, 0, and 2, negative 27, and a local maximum at 0, 5. Okay, and this is what the graph would look like. Yeah, this would be the local minimum. Okay, at negative 1, 0. The local max at 0, 5. And the other local min at 2, negative 27. Okay, and this is just a graphic. It shows us how the local max, how local min, neither occurs. So here we're seeing that we have increasing followed by decreasing, therefore we get the local max. A decreasing followed by an increasing, we get the min. If we have an increasing followed by another increasing, okay, that's a neither. Okay, it's not a maximum or a minimum. And the same thing if you have a decreasing followed by another decreasing, that would be another neither. concavity. Okay, function or its graph is called concave upward on an interval if the derivative is an increasing function on the interval. It is called a concave downward on I if the derivative is decreasing on the interval. Okay, so we see in this diagram concave up. Okay, the curve is opening upwards like an upwards parabola. Concave down, if the portion that has the downwards facing parabola, okay, that's like a concave down, and then followed by another concave up portion. Okay. In order to get concavity, in order to determine concavity, we look at the second derivative. Okay, if the second derivative is positive, then we say that the graph is concave up on that interval. If the second derivative is negative, then we say that the graph is concave downward on that interval. Second derivative test, this helps determine whether something is concave up or concave down. Suppose second derivative is continuous if the first derivative at c is equal to 0 and the second derivative is positive, then f has a local minimum at c. If the first derivative at c is 0 and the second derivative at c is negative, then f has a local maximum at c. Okay, discuss the curve with respect to concavity, points of inflection, and local maxima and minima. Use this information to sketch the curve. Okay, so first we'll find the first derivative. Okay, so that would be 4x cubed minus 12x squared. Then we'll find the second derivative. So second derivative would be 12x squared minus 24x. Now we'll set the first derivative equal to 0. We'll factor it, make it a little easier to solve. We can factor out of 4x. And we get a factor of 4x squared. And that'll leave us with x minus 3. For the second derivative, we can factor out of 12x. $12x times x minus 2. So now for the first derivative, to set this equal to 0, we know that x equals 0 and x equals 3. For the second derivative, we have x equals 0 and x equals 2. Right? Just set each factor equal to 0. Okay, and we get our critical points. So first derivative. So for first derivative, we have 0 and 3. Okay, so that means we could do test points at, we could do -1, we could do 1, and we could do 4. Okay, so for the first derivative, I'm going to use the factored form. So 4x squared times x minus 3. And now plug in these test points. So we have -1. We're going to square them. -1 minus 3. -4. It's -16. Okay, so that's negative. So decreasing. Plug in 1. 4 times 1 squared times 1 minus 3. So that's 4 times -2. That's -8. So that's another decreasing. Plug in 4. 4 times 4 squared, and then 4 minus 3. 4 squared is 16 times 4, 64 times 1, so 64 positive, so increasing. Okay, so we have decreasing followed by decreasing. We have decreasing, and it's decreasing followed by increasing. Okay, so there's nothing at 0. Okay, it's not a minimum nor a maximum. At 3, we have a minimum. Okay, so to get the minimum, plug 3 back into the function. So we have up here 3 to the 4th minus 4 times 3 cubed. So that's 81 minus 3 cubed, that's 27 times 4, 108. So negative 27. Okay, let's take a look at the second derivative test. That's for concavity. We'll use the second derivative. So we have 0 and 2. And that means we'll use test points of -1, 1, and 3. And we'll plug into the second derivative. This is second derivative test. Now, one of the things we have to note is we have possible inflection points at 0 and 2. They become inflection points when the concavity changes. So if the concavity changes from concave down to concave up, that's an inflection point. If it goes from concave up to concave down for the concavity, that's another inflection point. If the concavity does not change, then it is not an inflection point. Okay, inflection point only occurs when there is a change in the direction of the concavity. Okay, so let's determine the concavity. Let's take a look at the second derivative. So 12x times x minus 2. Okay, plug in -1. So 12 times -1, and then -1 minus 2. So that gives us -12 times -3, that's a positive 36. Okay, so concave up in this region. Let's plug in 1. So 12 times 1 times 1 minus 2. That's 12 times negative 1, so that's negative 12. So it's concave down in this interval. And then plug in 3. 12 times 3 times 3 minus 2. So that's 36 times 1, so that's 36. So that's concave up. Okay, so concave up. Okay, so we could do CU, concave up on negative infinity to negative 1. I should say negative infinity to 0. Concave up on 2 to infinity. And then concave down on 0 to 2. Okay, so let's find out those inflection points, since there were 2 of them. We're going to plug 0 and 2 in. Into our original function. So original function was x to the 4th minus 4x cubed. Okay, so 0 and 0, so that's 0, 0. Plug in 2. 2 to the 4th minus 4 times 2 cubed. So that's 16 minus 2 cubed is 8. 4 times 8, 32. 16 minus 32 is negative 16. Okay, so we have points of inflection at 0, 0, and 2, negative 16. What else do we have? We have a minimum at 3, negative 27. Okay, so we have decreasing function up to 0. Now 0 was the inflection point. And then it decreases again until 3, negative 27. Okay, so let's do a brief sketch of this graph then. Okay, it was concave up. And then at 0, 0 is an inflection point, so then it's concave down until 2, negative 16. Until 3, negative 27. Okay, so it'll look like this approximately. All right, questions? Okay, so if there are any questions, just email me. Okay, we'll discuss this further in class. Have a good day, have a good night. We'll see you soon.